All right, this week we are looking at Unit 10. Unit 10 is a little different than the other units in that we're going to get this done in 1 week. So you will do your lessons, you're also going to do your assessment. That being said, it's the only unit that we do this year where there's no project. So all you have to do is a multiple choice test. So there's this video for you to watch. There's some slides for you to go to. You're still going to do your Cornell notes, so I'd make a copy of that and kind of fill this out as you watch the video. You will turn those in by the end of the week. There's this multiple choice test. It's 15 questions. Each question's worth 2 points. And then, of course, you got your weekly check-in. So, again, just kind of looking at this, we're going to make sure you get those Cornell notes open. There's 5 lessons that we're going to go through. So you're just going to fill this in with the definitions, get the answer to these questions, and then make sure you have a key takeaway. And to kind of do that, we're going to go through these slides. All right, so lesson 1 is about algorithms. We've talked about algorithms a bit. An algorithm is a finite set of instructions that are followed to solve a problem. So specifically in this class, we define an algorithm as something that has sequencing, selection, and iteration. The point is there's multiple ways to write an algorithm that will answer a question correctly, right? These are some examples. So even though some are in pseudocode, some are using those diagrams. Some work in different ways. Essentially, these algorithms, they're kind of solving 2 different problems. If we were in class, we would really get into it. But even though they're all written differently, and there's 6 different algorithms up there, really 3 of them are answering one question, 3 of them are answering a different question. So even though they're written different, all 3 of them that are answering question 1 would all get to the correct answer. Right, so we can do the sequencing, selection, iteration however we need to. If we're going to write an algorithm or define an algorithm, we need to make sure that it has sequencing, selection, and iteration. So sequencing is when we put steps in a specific order. So sometimes in some other videos I've said sequencing means you have 2 or more lines of code. That's true, right? To have sequencing, you have to have multiple lines of code. The point is that you put those lines of code so that they complete steps in a very specific order that the computer can follow. Selection, that has always kind of been defined as our if statements. That is where we decide which step to do next. So if something's true, it's going to take one path. If something's false, it's going to take a different path. And then iteration, that's the use of loops to repeat a portion of our algorithm a specific number of times or until a condition is met. So if something's true, we might want to keep checking until it becomes false, and then we would exit that loop. All right, so it's important to know that every algorithm can be constructed using combinations of sequencing, selection, and iteration. Even though 2 algorithms might be written differently, we would consider them the same if functionally they produce an identical output given the same inputs. Right, so it doesn't matter how the code's structured. If I give it inputs and it produces the same outputs as a different algorithm with a different set of instructions, we say that they're the same. Right, this is kind of fundamental to our algorithm's success, this idea of sequencing. So algorithms must be executed in a specific order. Changing the sequence, it changes the logic, and it could prevent the goal from being met. Right? And then, you kind of have this idea that there's multiple ways to write these algorithms, right, for the same problem. So 2 of you could write an algorithm to select a movie to show someone based off the genre that they want to watch that night. As long as, given the same inputs, your code is producing the same outputs, the actual algorithm could be written differently. We would say they're the same, but, a single problem can be solved with different algorithms, essentially, which kind of gets us into lesson 2. So now that we kind of know what an algorithm is, we start talking about how efficient it is. When we're talking about efficiency, that is a measure of how many resources, so it's usually time and steps, an algorithm uses as the input size grows, right? So how many steps is it going to have to take, and how much time is it going to take? The less steps, the less time, we say that algorithm is more efficient. So for this lesson 2, there's 2 particular algorithms that they want you to know. One of them is the linear search. So a linear search is an algorithm that checks every element in a list one by one until a target is found. What you'll notice about the linear search is it's kind of just this straight line. So we get into this idea of like best case and worst case. Where best case, that's the fewest number of steps an algorithm could take. Not that it will, but that it could. Worst case is the maximum number of steps an algorithm could take. Right. So if I had, this algorithm that was going to check 6 different inputs, my best case would be 1. I could get lucky and find it on the first one. My worst case scenario is it's going to take 6 steps. And by step 6, I either found it or I've realized it's not in my list. All right. So that's why we call this the linear search, because if there's 10 inputs, there's worst case 10 steps that I would have to do. Kind of the next one that we talk about is this idea of binary search. What's important about binary search? When we're doing a linear search, if we're checking numbers or we're checking strings, that list that we're searching through does not have to be sorted. So it can just be in any order. Binary search is extremely efficient, but it only works if your list is sorted. So a binary search is a search through a sorted list that starts in the middle and eliminates half each time. The idea here is I have this sorted list of numbers from 117 up to 833. I am looking for the number 705. So because my list is sorted, I can start in the middle. All right, so I'm going to say, is 705 equal to 410? It's not. So then I would ask, is it less than or greater than? So 705 is greater than 410, which basically means 410 and any number to the left, I can ignore. Because my list is sorted, I know 705 is greater than 410, so it cannot be to the left of 410. So I would essentially get rid of all of those numbers, and then I would look in the middle from what's left, right? So in this case, I still have 705, 716, and 833. So I would compare 705 to 716. Again, it's not equal to, it's less than. So I know it's not 716, and I can eliminate any number to the right because my list is sorted. So 716 and 833 go away, which leaves me one number to check, which is 705. And in this case, I know 705 is equal to 705, so I found it. So you can see this is more efficient than a linear search. If it was a linear search, I would have checked 117, 232, 245, 410, and I would have found it on the 5th step. Using this binary search, I essentially found that number in 3 steps. All right, so if we were kind of comparing these efficiencies, you can see this binary search kind of flattens out pretty quick, because binary search, it's a very efficient algorithm if the numbers are sorted. So as the number of inputs increases to a super large number, my binary search can still find it relatively quick. What's important to know, like the reason it's called binary search is because the number of bits that it takes to make the number of inputs that you have, that is the maximum number of searches that you would have to do. That is your worst case. So if I was going to make the number 7 in binary, which you could write this out, you would use the first 3 bits, 4, 2, and 1. All right, that makes the number 7. 3 bits means worst case scenario, I'm going to have to do 3 checks. Right? Obviously, my best case is still 1. But that's where the name of this search comes from. Just remember, it's for a sorted list, and we just keep comparing the middle. So this is kind of, your comparison of the two, so you can see that a binary search is more efficient than a linear search as the number of inputs grow. Don't forget, when we're talking about efficiency, we're really talking about the algorithm that requires fewer steps to complete as the input size increases, right? As the input increases, the less steps, it's considered more efficient. So that kind of gets us to lesson 3. This has to do with unreasonable time. So if we were in class, we would kind of be comparing 2 different raffles. One of them is called the pair raffle. The efficiency for this, we also call this the polynomial algorithm. So on a polynomial algorithm, the rate of growth where the steps are proportional to the power of the input size. So it's n to the second, n being the number of steps. So if I have, 5 checks, then it's 2 to the 5th. right? That's how many checks I would have to do. You can see this one, it becomes inefficient pretty quick. And what we start trying to determine is, can I finish this in a reasonable amount of time? So exponential algorithms, that's when the rate of growth doubles or more with every single new addition to the input. So now instead of being n to the 2 like a polynomial, it's 2 to the n. And with regards to time, we say an algorithm will finish in either a reasonable amount of time or an unreasonable amount of time. If it's a reasonable amount of time, that's anything with a polynomial growth or less. So really we're talking about a linear search, a binary search, or a polynomial search. Once we move past polynomial and we get to exponential, where it's 2 to the n, we then say it's unreasonable, right? So unreasonable time is an algorithm whose exponential or factorial in its growth. So it's 2 to the n or n exclamation, the factorial. It just grows too fast to be practical for large data sets. Right, so this is the exponential growth. You can see this one, does kind of go out a little bit and then comes up. This one, the exponential starts going up pretty quick, right? This is 2 to the n. And again, we say an algorithm is reasonable if it's polynomial or less. So for our class, if it's linear, binary, or polynomial, it's reasonable. If it's exponential, it's unreasonable, meaning it's not going to finish in a reasonable amount of time on larger data sets. Right, so it's not that computers can't solve unreasonable problems. They can solve unreasonable algorithms, so something that's exponential or higher. But usually for computers, we only want to run them when the number of inputs that we're searching is relatively small. Because even if a computer can finish it, it might not be able to finish in a reasonable amount of time, meaning it could take that computer a couple weeks to solve that problem. There's efficiencies out there where it will take the computer months or years or a lifetime to finish that problem. So again, it's not that it can't solve it, it's just not going to solve it in a reasonable amount of time. So this is kind of our chart that looks at those algorithms together. One thing that kind of a real life situation that we use to talk about this is what we call the traveling salesman problem. This idea that like you have a salesman, he has to go from house to house to house. And maybe there's, 100 houses that he has to visit on a certain day. You want to find the most efficient route for him to travel. When it's 2 or 3 houses, that's fine. You can figure that out. When it's 100 houses, it starts getting really hard because you have time of day, traffic, stop signs, stop lights. Trying to figure out the most efficient route to get that salesman from point A to the end, reaching all 100 houses along the way, becomes super hard to do. All right, so kind of taking that idea a little bit further, we get into the limits of algorithm. So again, here's that traveling salesman, right? He's in the greenhouse. He's got to visit all the houses. It takes him so many steps to go to each one. We can do this when it's a low number of inputs, but when it starts getting bigger, it starts getting really hard. And at some point, we just need to kind of cut it off. So when we're dealing with these algorithms and the idea of reasonable or unreasonable, we get into this question, is our issue that it's a decision problem, meaning is there a path? Can we make a decision? Or is it an optimization problem? Optimization, it's a problem with the goal of finding the best solution among a ton of possibilities, right? So we kind of want to say, is the problem decidable? A problem for which an algorithm can be built to provide a definitive yes or no answer for all inputs. That's a decision problem. There is a yes or no answer. That's a decision problem. The optimization problem, that's a problem with the goal of finding the best solution. And that's where we tend to have issues when we get into exponential and factorial algorithms. So an undecidable problem, it's a problem where no algorithm can be built that always leads to a correct yes or no answer. We simply don't have a way to do it yet. It's undecidable. And that leads us into this idea of a heuristic. A heuristic is a shortcut, right? we're going to write an algorithm that's good enough. I can't, because it's undecidable, because there's an optimization issue, because it won't finish in reasonable time, I need to still have a solution for this. So rather than trying to find the perfect solution that could take years or a lifetime to figure out, I'm going to settle for something that's good enough, right? We call that a heuristic. So this idea, like, why can't a faster computer solve an undecidable problem? It's usually a logical limit. It's not a hardware limit, right? There's just no amount of hardware speed can solve a problem proven to have no algorithmic solution. So when a problem is decidable, but finding the absolute best or exact solution takes an unreasonable amount of time, that's when we look for a heuristic. You can think of that traveling salesman problem, right? It's an optimization problem that is decidable but becomes unreasonable as the number of cities increase, right? It's just too much for us to try to figure out. And then understand heuristics don't find the best answer, they find one that's good enough. So to kind of deal with this idea of decision problems, optimization problems, heuristic, reasonable time, unreasonable time, we get into the idea of distributed algorithms. So we talked about an algorithm having sequencing, selection, and iteration. On the sequencing part, historically in this class, we've always seen you write code in a certain sequence, it finishes step 1, goes to step 2, goes to step 3. Sometimes we talk about algorithms that will run in parallel. Right, so parallel computing is the model where a program is broken into small pieces, some of which can run at the same time. This is in contrast to a sequential computing issue, where a computational model that it operates where each task is performed one at a time in a specific order. So I could have an algorithm, right? I could make this more efficient. I could increase its time efficiency by trying to break some of the steps up so they can run at the same time. So maybe I've got part A, I can't run part B until part A finishes, but once B finishes, I can run C and D together. And then once C finishes, it can run E. When D finishes, it could run F. And then once these two finish, they could then come back together to finish this one. So whereas, originally if I ran this all in sequence, I would be doing 1, 2, 3, 4, 5, 6, 7 steps, one after the other. I've compressed it down to where now, steps 3 and 4 run in parallel. So I'm really finishing in 5 steps now, not 7 steps, right? So this is parallel computing or distributed parallel computing, however you want to say it. But again, it's this idea of kind of breaking the algorithm up so some steps can be run in parallel. Distributed computing is when we have multiple devices that are running different parts of a program over a network. So maybe one computer by itself can't run this algorithm, or it can't compute this calculation that I need. So I get a bunch of different computers spread out, across the school or across the city or across the globe, and they're working together to try to solve this problem. In either case, whether you're going parallel or distributed, there is this concept of speed up time, right? Speed up time is when you go from like sequential to parallel computing, how much time, like, what did you save, right? So the formula for speed up time is basically the ratio of time taken to run an algorithm sequentially compared to running it in parallel. So we say the speed up time is the time sequential divided by the time parallel. So in this case, if it ran 60 seconds sequential, 40 seconds parallel, I take 60 divided by 40, it gives me 1.5. So my speed up time is 1.5. All right, so understand we can improve our efficiencies through parallel and distributed computing. It doesn't always help. Like sometimes most algorithms have a portion that cannot be run in parallel, which eventually limits how fast the program can go regardless of how many processors are added. There's benefits to distributed computing. It allows for the processing of massive amounts of data that would be too large for a single computer to handle. But at the end of the day, parallel computing is more complex than sequential because it requires coordinating multiple tasks at once to ensure they sync up correctly especially for the parts that can't be split, right? And you do get a return of investment on this speed up time, but it's never going to just keep going forever. At some point, we can't add any more to it. So that's where you see these lines kind of leveling out, right? At some point, adding more computers or trying to break the algorithm up even more just doesn't help us. So our goal is to always try to get to the point where it starts to level off, but not to go into the part where it levels off. Because over here, I'm just wasting resources. I'm not getting any benefit from adding more. Over here, I was still seeing a little bit of benefit. All right, so I want to try to get in here. All right, so there's your terms for lesson 5. So again, that was a quick run through of lesson 10. Make sure you fill out those Cornell notes. For this week, again, you just have the 3 assignments, so you're going to turn in your Cornell notes. There's a Unit 10 multiple choice test. You'll take that. And then don't forget to do your weekly check-in. And as always, if you have any questions, come by and see me.